Hi, and welcome to 10.5b Electric Fields 2. In this lesson, students will be able to create a model of the electric field around various charged objects by drawing electric field lines. So here are the rules for drawing electric field lines. This is the model that we're going to use to represent the electric field that we talked about yesterday. Rule number 1. Use a positive test charge to determine the direction of the field. Rule number 2, lines start on positive charges and they end on negative charges. That's rule number 3. Rule number 4, the number of lines per unit area is proportional to the strength of the electric field. So if the lines are closer together, that means that the field is stronger. If the lines are further apart, that means the field at that point is weaker. Rule number 5, lines cannot cross each other. So let's put those rules into action and draw the electric field lines around some various charges. Your goal for today is to be able to draw the electric field around the following charges. A positive charge, just a positive single point charge. What does the field look like around that? And we want to say, where is the field the strongest? And then we're going to do a negative charge. What does the electric field look like around that? How can we draw the lines? And then again, where is the field the strongest? Then we're going to have two charges, a positive charge near a negative charge. We'll draw the field lines around that situation. And then a positive charge and a positive charge. And then where is the field 0 newtons per coulomb? And then a negative and a negative. Where is the field 0 newtons per coulomb? Try to think of like what that might look like. And then between two oppositely charged plates. So instead of just point charges, then we'll do an example where there's two like metal plates, and then we'll draw the field between those oppositely charged plates. And for each case, we want what direction would a positive test charge travel? So we'll draw a little positive test charge and show the direction that it would go. And then also, what direction would an electron travel, a negative charge, if it was placed in that field? Oh, and then between, for number 6, we'll say, where is the field the strongest? So those are the rules on the top there. And we have a positive charge. And you can draw this on your own. Like if I was going to draw this, it would be like this. Boom, boom. And then you could draw the lines. So if you're taking notes, which you should be, you'll draw the lines that pop up in a second. So the question we want to ask ourselves is, where would a positive test charge go if it was near this positively charged sphere? Where would it go? Picture it in your head. It would be repelled away, so it might go like that. Now, if you put positive test charges all around this positive charge, what direction are all of these positive test charges going to go? They're going to go away. So you should draw in your notes, let's draw these electric field lines. And they're all pointing away, all right, because we did number 1, we used positive charges. We're going to start on positive and go out. So all of these get arrows pointing away like that. And then we don't have any negative charges, so we can't do number 3. And then we'll talk about the lines per unit area for this thing. Okay, and then what direction would a positive charge and a negative charge go? So if you had a positive charge, we already said we would point it in that direction. If you're taking notes, you can draw this in. But that's not part of like what makes an electric field line. Like this really shouldn't be there. Once you have these lines, then boom, you're done drawing the electric field lines. I'm just going to add some more into our diagram so that you get more concepts in your notes. This is for your notes. Now, if you had a negative electron, what direction would this negative electron go? It would be attracted to the positive charge, right? So even though the electric field lines are pointing outward, yeah, that means the field would push this positive charge away because we drew it in the direction that a positive charge would go. But electrostatics is cool because you have positive charges and negative charges that act in opposite ways. So this will be going against the electric field lines because it is attracted to that positive object. Okay? Then this is kind of talking about number 4 here. The number of lines per unit area is proportional to the strength in the field. I have a unit area, and I'm going to draw the same side box but further away. And we can see that the electric field intensity is larger in A than in B, because look at the number of lines per unit area. We have 1, 2 lines in here, and then here it's further away. That's what number 4, that's like I'm showing you what does 4 mean, Mr. Nangle? That's what it means. So basically, the closer the lines are to each other, the stronger the field. And the further apart the lines are, the weaker the field. Okay? And remember, like we did in the last lesson, the electric field doesn't only lie on this line that we drew. We're using these lines as a model to represent the more nuanced, like it's in the region, and I use the colored light to represent that. But that's hard to draw. So instead, we draw these electric field lines as a model to represent that concept. Okay? Then it says E, the electric field strength, is the same along line C. This is what's called a line of equipotential, actually. All right, so it's the same field intensity because it's the same distance away. And all the field lines are the same distance away from each other along that line. Cool. How about for a negative charge? What would happen to a positive test charge if you bring it near a negative charge? These unlike charges are attracted to each other. So where would the positive test charges go? They all are attracted to the negative test charge. So again, if I was going to draw this, like you should be drawing in your notes, the lines start on positive charges and end on negative charges. So they're going into negative, out of positive, into negative. This is where a positive test charge would go. So again, we were done drawing the electric field lines, but now we're just adding some more in for our notes purposes. So this is just confirming that a positive test charge goes in the direction of the field. A negative charge would go in the opposite direction from the field, again, because these are repelling each other. And then we could still do the same thing. The closer you are, the stronger the field intensity. And then if you stay the same distance away, the field intensity is the same. All right, what would this look like between a positive charge and a negative charge? You might have seen this type of thing maybe with magnets. What if this was like the north pole of a magnet? This is like north, and this is the south pole of the magnet. These two are attracting each other, right? So what would that look like? Did you ever do the iron filings thing before with the two magnets? We'll do that later. All right, but if you have a positive charge here, it gets, what direction would it go? Pause the video and think about it, because you really need to be able to visualize where a positive charge would go in these cases. So it's being repelled by this positive charge, and it's being attracted to that negative charge, so it's just going to go straight across. And then think of like if you had them over here. This wants to be repelled straight away, like we did before when it was all just outward. All right, but now it has, this is affecting the electric field near it as well. So it's also being attracted to this negative charge. So what ends up happening is it looks like this. Boom, nice. And then this is my little friend. I always forget, hey, look at this. It looks like an alien winking at you. Nice. Well, what if, is it only in between the two? Like, no, the electric field is in the universe. So let's see. If it's on this side, then they're repelled away, but eventually they'll get sucked back into that side. So that's what the electric field lines look for that. Mr. Nagel, how the heck am I going to draw that? You just go, I'll draw a small positive, negative. You go over a little bit more. Actually, I'll make these two are like closer to each other. And then it gets further away. That's nice. There's our buddy again. And then it goes like, wow, he has a big head and a big mouth, and then out until you can't anymore. Out of positive into negative. Out of positive into negative. You just try to make it symmetrical. It's like art. And then put one off straight to the left, and then in like that. Wow, look at that drawing. Very nice. Okay, let's answer some, let's talk about the concepts a little bit more, right? So where would a positive charge go if it was placed right there? Probably go to the right. And then what about a negative charge? Remember, the negatives go against where the field is pointing because the field is drawn where a positive charge would go by convention. All right, now let's do the unit area thing. Look at all those lines there, as opposed to over here. Same area, lines per unit area. Let's see, we have 1, 2, 3, 4, 5 lines. This only has 3. So what can we say? The field is strongest between the poles. When you have a situation like this, the electric field intensity is larger in between the charges. Okay. What about if it's two positive charges? Think about where a positive test charge would go. It gets pushed away, right? It's repelled. And just like these, they all get repelled away. Now this one's going to be repelled. It's going to try to get, oh, I don't like this. Let me go far away from this one. But then it encounters the electric field from this one. And then it's like, oh, I don't like that either. So it ends up going this way. And this one ends up going this way. And it looks like this. Beauty. Very nice. Very nice. If I was going to draw that, I'd probably go like this. Positive, positive. We're going out of positive. And I go just like boom, boom. Try to make it symmetrical. Don't cross the lines now. And then space them out. Little less curve this way. Out. Little less curving going on. Little less curving going on. Something like that. This is like kind of artsy like this. Gotta have a good eye for, oh, I did that the opposite direction. You gotta have a good eye for what's going on. Okay? I didn't draw any lines in between over here. What's going on in between those things? Let's see. Well, the positive charge gets repelled away in the direction of the field. And the negative charge, what direction is the negative charge going to go? Opposite those field lines. And then what can we say about this point in the middle? Are there any field lines there? Like, if they're equal magnitudes of charge, this one's going to point this way, this one's going to point this way, and they cancel each other out right in the middle. At point P, you have 0 newtons per coulomb. They are canceling each other out. The electric field intensity is 0 right in the middle of two like charges. Well, what if they're both negative? If they're both negative, what happens to the positive charges? They get attracted to them. So all these go that way. Same thing, but all you're doing is just changing the direction of the arrows. So I guess I could do that quickly too. Do this with me. Are you taking notes? Curve into negative. Out of positive into negative. That's like one of the main ideas. Out of positive into negative. Boom. That's nice. Try to draw like very symmetrical here. Boom. I drew less lines this time, but it's still symmetrical, so technically that's fine. Remember, this is just a model for what's going on. Okay, so again, a positive charge goes in the direction of the field lines because by convention, the field lines are drawn where a positive test charge would go, and the negative charges therefore go in the opposite direction of the field lines. And now at point P, if you had a positive charge here, it would be attracted to this one, and it would also be attracted to this one. And if these charges are equal magnitude, which they are, those two vectors cancel each other out. So it's 0 newtons per coulomb right in between two like charges again. Beautiful. Well, how about between two oppositely charged plates? What does the electric field look like there? If we have a positive test charge, what direction will the positive test charge go? If you didn't pause your video before, please pause it now and think about it. Where is this charge going to go? Do you have a guess? It's going to go straight down because it's repelled by the positive plate and it's attracted to the negative plate. And the lines, whoa, hold on a second. The lines look like they're pretty equidistant. So the electric field intensity is the same at points A and B, or in A and B, the regions. It's the same. The electric field intensity is equal at all points in between two oppositely charged plates. What? Even like over here, like 1 is so much closer to this. How could that be an equal? Shouldn't this be affecting it more than like 2 or 3? What's going on there? How can the field intensity be the same? So, you have this positively charged plate. That is true. And at point 1, if you put a positive test charge there, it would be repelled more than at point 2. See, it's a smaller vector. And at point 3, you're far away from this. So, yeah, you're not going to be repelled as much. See where I'm going with this? So the repulsive force decreases as you get further away from the positive one. But what's happening as you get further away from the positive one? You're getting closer to the negative one. And if you have a positive test charge, it's going to be attracted to that negative plate on the bottom here. So if you're far away, you're not going to be as attracted, but as you get closer, you're more and more attracted to the negative plate. And the electric field is the combination of both. So the attractive forces increases as the repulsive force decreases. The sum of the forces remains the same. Let's do the vector sum of those red and blue arrows. How do you add vectors? Head to tail, head to tail, head to tail. And the magnitude of the sum is the same. So that means the electric field strength is the same in between, at all points in between those two oppositely charged plates. All right, so we do have a challenge question here, and there's less than 20 minutes into the video. So if you want, you could pause this, check it out. It's basically just the same magnitude of charge, and they're oriented like this. 7.5 centimeter square, and they want to know, determine the magnitude of the net electric field that exists at the center of the square. So if you want a little challenge, pause the video, think about it, and then I'll go over it pretty briefly. So here's the idea. The electric field intensity is equal to KQ over R squared. And all of the charges, the magnitude of the charges are all equal to each other. And since that point that they're asking about is right in the middle, the distance between the point and the charges are also all the same. So the magnitudes of the electric field strength of like A and the electric field strength brought by B and C and D, the magnitudes are all the same, but what direction are they pointing? What is the direction of the electric field intensity for each charge? So let's think about each one individually. If we put a positive test charge here, is it going to be attracted or repelled by charge A? It's a positive test charge, so the electric field points towards A. How about if a positive test charge is here, how does the electric field, what direction is the electric field brought by B? It's repelling it away. Same with C. It still repels it away in the same direction as EA, because remember, this was a negative. We made this the negative charge. So these are both pointing in the same direction. but the direction of the electric field brought by D is in the opposite direction of B. So if you just look at the direction of the electric field by B and the direction of the electric field by D, you can see that they're canceling each other out because, again, they have the same magnitude, the same charge, and the same distance away. But we can see from this diagram that they're pointing in exactly opposite directions, so they're going to cancel each other out. And now all we have to do is analyze the electric field for A and C. So let's take a look at the electric field intensity of A. That's equal to K times the charge of A divided by the radius squared. Well, what the heck is the radius? What's the distance between those? We should probably try to draw a triangle, and the half of 7.5 centimeters is equal to 3.75 centimeters, and that's going to be able to give us the radius when we do the Pythagorean theorem. So that distance is 5.3 times 10 to the negative 2 meters. You plug that in for R. Don't forget to square it. They told you the magnitude of the charge, and we know K, the electrostatic constant. That gives us a magnitude for the electric field of A as 9.9 newtons per coulomb. We do a very similar thing for C, and C is going to give us a charge, equal charge, same radius, same electric field strength, 9.9 newtons per coulomb. So then how do you figure out the net electric field? You just have to add those two together since they're pointing in the same direction, and you get a net electric field intensity of 19.8 newtons per coulomb. Again, B and D cancel each other out, so we don't have to include that in our calculation for this example. So just a note about the magnitude, right? When I did the Coulomb's law, we talked a bit about how if this is negative and that's positive, you get a negative for the answer, and that indicates the direction as being attractive. And if they're both negative, then you get a positive here, and the positive means they're repelling each other because, again, all right, but that's actually really only if it's in one dimension. If they're in line with each other, then you could use that little trick, and that'll indicate a negative and positive will indicate a attractive or repulsive force. As soon as you go into the two-dimension things, the sign doesn't really mean as much. It's just the magnitudes of the charges that we want in here, and the same with our electric field strength formula. Technically, we really just want the magnitude of the charge, and then we'll have to figure out what the direction of the field is based on what the diagram looks like. Again, if it's a one-dimensional type of situation, you can use the positive and negative as a way to indicate if it's attractive or repulsive. But technically, you want to use the magnitudes. All right, that's the real deal. Anyway, that's about it. Thanks for watching and have a great day.